Bismillahirrahmanirrahim. Dear students, grade 11, and the lecture number is 63 today. And we are going to start lecture number 11, electrochemistry. Lecture number 63, and chapter is 11, thermochemistry, and class 11, grade 11. So, according to your reduced syllabus, we are going to start oxidation and reduction. Thermochemistry. The first topic is Hess's law. The first topic is Hess's law of constant heat summation. Thermodynamics. Chapter number is thermodynamics, and topic is Hess's law. Chapter number 11, thermodynamics. Now, if we are going to go the definition of thermodynamics, the study of all types of energy changes associated with the chemical and physical changes is known as thermodynamics. The study of all types of energy changes associated with the chemical and physical changes is known as thermodynamics. So in the chemical reactions, we are seeing two types of changes. One is exothermic reaction and another is endothermic reaction. In exothermic reaction, heat is evolved from the system to the surroundings. In the endothermic reaction, the heat is absorbed from the system in the surroundings. This is thermodynamics. So, the branch of chemistry which deals with heat change of chemical reaction is in a chemical reaction, and a thermochemical reaction is called thermochemistry. So, we will be talking about the heat is evolved and heat is absorbed. According to the reduced syllabus, chapter number 11, thermochemistry, the first topic is Hess's law of heat constant summation. G.H. Hess in 1840 put forward a law is called Hess's law. This law states that enthalpy change in a chemical reaction, enthalpy means heat contained in a system, H capital, change delta H. So enthalpy change in a chemical reaction is same whether the reaction takes place in a single step or several steps, many steps. When the enthalpy change in a first step, when the reactants change into completely product, the chemical reaction complete in the first step, delta H change in enthalpy must be equal when the same chemical reaction completes in several steps is called Hess's law of heat constant summation. So dear students, when we are going to write in the mathematical form, sigma, capital sigma, change in enthalpy is equal to 0. Cycle. Sigma change in enthalpy cycle is equal to 0, means forward and reverse. In one state and many states, both sides must be equal, then it should be 0. Suppose we have a chemical reaction, A reactant changes into a B product. There is a delta H. So in one step number 1, and this is called initial state, and this is called final state. Initial state to final state, A changes into B product. The change in enthalpy takes place either endothermic reaction or exothermic reaction. In other words, if this reaction completes into many steps, delta H1. So this is the first step. A changes into C, and delta H2, C changes into D. Delta H3, D again changes into B. It means that this enthalpy change, when the chemical reaction completes in a first state, initial state to final state, must be equal to sum of these delta H1 plus delta H2 plus delta H3. So this is called Hess law of constant heat summation. Hess's law of heat constant summation is called an enthalpy change in a chemical reaction, same whether the reaction takes place in a single step or several steps. So this is the Hess's law. Now we have examples. Two examples are given here. So now I am going to explain these two examples. Example number 1, 11. Example number 1, 11.3. Oxidation of nitrogen. Nitrogen gas plus 2 moles of oxygen gas to form 2 moles of nitrogen dioxide gas. Change in enthalpy at the standard states is 68 kilojoule. This is A into B, initial state and final state. The chemical reaction complete in one step. According to Hess law, if this same chemical reaction completes in more than one steps. So this is the step number 1. Nitrogen gas, oxygen gas in the limited. The first form, nitric oxide or nitrogen monoxide, delta H 180 kilojoules. Step number 2, step number 2, 2 moles of nitric oxide gas, again oxygen gas to form nitrogen dioxide gas, delta H naught is equal to minus 112 kilojoules. First state is endothermic and second state is exothermic. Plus sign or no sign indicate endothermic, negative sign indicates exothermic. So when you are going to add these two steps, nitrogen monoxide or nitric oxide on product side and reactant side, same moles consumed, cancelled out. 1 mole of nitrogen gas, oxygen 1 mole, oxygen 1 mole, same side, 2 moles of oxygen, changes into 2 moles of nitrogen dioxide. So delta H is equal to delta H1 plus delta H2. So that's why delta H is equal to exactly 68 kilojoules. Means delta H is equal to delta H1 plus delta H2. So delta H is equal to 68 minus 112. So you will get 68 kilojoules. So this is the example number 1. According to Hess law, if the chemical reaction completes in the one state, initial state to final state, and the amount of energy is absorbed in kilojoules 68, and the same chemical reaction completes in more than one step, 2 steps. So this is the nitrogen gas and oxygen gas to form 2 moles of nitrogen monoxide gas in delta H1 180 kilojoules. Then the chemical reaction is not still complete in the step number 2. 2 moles of nitric oxide and oxygen gas to make the 2 moles of nitrogen dioxide. So delta H2 is equal to minus 112 kilojoules. 2 moles are cancelled and you will get 100% same equation. And delta H, according to Hess law, delta H is equal to delta H1 plus delta H2. When you add, you will get the same 68. So dear student, this confirmed that enthalpy change in a chemical reaction is the same whether the reaction takes place in a single step or in several steps, many steps. This cycle is complete. Because of the syllabus is reduced, many things because of when the syllabus is going to be arranged by the educationist, by the subject specialist, there is a sequence. There is a sequence of topics between each other. So because of this is a special environment, special conditions due to the COVID-19, so government of Pakistan is going to be reduce the syllabus due to different situations. So that's why I'm not going to detail go back because of these topics are going to be related with each other, just like state function. This is the initial state and final state. The state function means the chemical or physical change only depends upon initial to final, not intermediate. Initial, 1 mole of nitrogen gas, 2 moles of oxygen gas to form 2 moles of nitrogen dioxide. The amount of energy is absorbed 68 kilojoules. Independent of path. State function means the change, chemical or physical, only depends upon initial to final state. Not a independent path is called state function. So change in enthalpy is a state function, change in temperature is a state function, change in pressure is a state function, change in energy is a state function. These are the state functions because they only depend upon initial to final states. Dear students, there is a you have to draw the potential energy diagram. We have the potential energy diagram for this system. So I am going to run this, then I will draw potential energy diagram. So according to the potential energy diagram of the example number 1, energy cycle, we call energy cycle. This energy increasing from bottom to top, or you can say enthalpy change in kilojoules. In energy cycle, you have nitrogen gas plus oxygen gas. Now students, when nitrogen and oxygen gases, they combine in one state to give us 2 moles of nitric oxide. Or if we are going to here one step we show one line energy same. This is a 1 mole of nitrogen gas plus 2 moles of oxygen gas. This is the first step where you will get the product delta H. So delta H. So energy is going to be increased. Delta H energy is going to be increase endothermic reaction and 68 kilojoules. 68 kilojoules, and you will get the product 2 moles of nitrogen oxide gas. This is a initial state to final state in the one state chemical reaction completes. One state chemical reaction completes 1 mole of nitrogen and 2 moles of oxygen gas to give a 2 moles of nitrogen dioxide. The total amount of energy is absorbed 68 kilojoules. Then this chemical reaction completes in the 2 steps. So step number 1, nitrogen and oxygen. Nitrogen and oxygen. Now in one step the amount of energy is absorbed more, means delta H1 180 kilojoules. That's why higher amount of energy is absorbed more, and you are getting 2 moles of nitric oxide or nitrogen monoxide. Then this nitrogen, 2 moles of nitrogen dioxide, the second step is exothermic reaction. The second step is exothermic reaction when these 2 moles of nitric oxide, 2 moles of nitric oxide gas and more oxygen gas. So you are seeing that the amount of energy will decrease. The reaction is exothermic. So delta H2 will be equal to minus 112 kilojoules. So minus 100 kilojoules. So sum of these 2 steps give 68. This is the initial state when 1 mole of nitrogen and 2 moles of oxygen react to give a 2 moles of nitrogen dioxide, and total amount of energy is absorbed, which is called delta H. This is a change in enthalpy. Then this chemical reaction completes in the 2 steps, 1 step and this is the second step. In 1 step, this is the nitrogen gas plus oxygen gas, 1 mole each to form 2 moles of nitric oxide, and this is a change in enthalpy 1, which is 180 kilojoules. Then delta H1 plus delta H2, this is the 2 moles of nitric oxide and oxygen mole to form a 2 moles of nitrogen dioxide. So this is the final product, and this process is an exothermic reaction. So that is why delta H is equal delta H1 plus delta H2. Both sides must be equal. So this Hess's law is going to be proved. This is an energy cycle diagram according to Hess's law. We have another example also. Write down in your copies. Now example number second. In example number 2, 11.4, 14. This was 11.3 and this is 11.4. In this example, carbon solid, 1 mole of oxygen to give a 1 mole of carbon dioxide gas, delta H is minus 393.5 kilojoules. This is a delta H. Then this chemical reaction completes in 2 steps. Step number 1. In step number 1, carbon solid plus half oxygen gas, limited oxygen gas to form carbon monoxide, because these values for the 1 mole. So this is the delta H1 minus 110.52 kilojoules. In step number 2, this carbon monoxide gas plus half oxygen gas to form carbon dioxide gas, and delta H2 is equal to minus 282.98 kilojoules. So when you are going to add these 2 equations, carbon monoxide intermediate appears on one side, product side, and appears on the reactant side, so it will be cancelled. So carbon solid, half and half full mole of oxygen gas to form a carbon dioxide gas, and this delta H is equal to delta H1 plus delta H2. When you add both, you will get minus 393.51 kilojoules. Same. If the chemical reaction completes in one step, or it completes in the 2 steps, sum of these steps delta H must be is equal to delta H1 plus delta H2. This is proved from the Hess law of constant heat summation. Students, there is another very important thing, especially in this chapter and equilibrium chapter, but you can write generally or write the states of the reactants and products must, because here we are talking about the changing liquid into gas, gas into liquid, liquid into solid. So they have different enthalpies. Just like H2O water, in a gaseous state, it has a different enthalpy. If it changes into ice, delta H ice, H2O in solid, it has a different. If water liquid, it has a different. So that is carbon diamond, it is a different. Solid. Carbon diamond graphite, it is a different. That's why, because of we are involving here their energies, their values, so in the calculation, so that's why it is very important for you to write their states when you are mentioning reactants and products in the balanced chemical equation. So this is example number 2. So now same, I will draw the cycle for this one, energy cycle. Now, if you see the energy cycle for this chemical reaction, example number 11.4, you are seeing that first step is exothermic, which is the delta H. So, carbon, solid plus oxygen gas. This is the enthalpy change in kilojoules. So, dear students, carbon, solid and oxygen gas when going to be combust, burn to give a carbon dioxide gas. Exothermic reaction, delta H naught minus 393.5 kilojoules, and you will get carbon dioxide gas. This is the step number 1. Means complete. When the chemical equilibrium reaction is complete, you will get full products. Delta H. The same chemical reaction complete in more than one steps. So, carbon, solid, of oxygen gas. Now, this will be changed into carbon monoxide. Again, exothermic reaction. So this is the delta H1. Delta H1 will be minus 110.53 kilojoules, and this changes into carbon monoxide gas. This change into carbon monoxide, this is the delta H1. So when this carbon monoxide again oxidizes, so it is going to change into delta H naught to minus 282.98 kilojoules, and we will get carbon dioxide gas. So when the chemical reaction complete in the one step or several steps, the delta H must be equal to sum of those steps. So this energy is increasing, this is the exothermic reaction must be decreased when the chemical reaction complete in the delta H, carbon, solid, oxygen gas to form 1 mole of carbon dioxide gas, and this chemical reaction complete in 2 steps. This is delta H1, carbon and half oxygen in complete combustion, and you will get carbon monoxide gas, and minus 110.53 kilojoules amount of energy is going to be released. Then carbon monoxide again oxidized in half mole of oxygen to give a 1 mole of carbon dioxide gas. So this is delta H minus 282.98 kilojoules. So according to Hess law, delta H, their standard states, so must be equal to delta H1 plus delta H2. So this is the confirmation from these two examples that Hess's law is going to be obeyed. So dear student, this is about the Hess's law. So now Hess's law is useful, practically useful to calculate the enthalpies in indirect form, indirect way, indirect methods. to calculate the enthalpies in indirect way, because there are some complications. The complications are here. This is the carbon tetrachloride. This is the aluminium oxide. This is the boron trioxide. So according to experimental observations, the enthalpy of carbon tetrachloride, tetrachloromethane cannot be measured directly. Enthalpy change of carbon tetrachloride or tetrachloromethane cannot be determined directly. If you go back in grade 10, how this carbon tetrachloride was formed? First step, second step, third step, fourth steps. Start from methane. Take a methane, pass chlorine gas in a diffuse sunlight, you will get chloromethane. First step, delta H change. This chloromethane, again chlorine gas, and diffuse sunlight, you will get dichloromethane, then trichloromethane, last is a tetrachloromethane. We can't prepare directly. In indirect method, enthalpies of some compounds can be determined. So this is the usefulness for this one. Also, enthalpy of formation of aluminum oxide also cannot be determined, because when you are going to react aluminium plus oxygen to form aluminum oxide, so when the chemical reaction is initiated, started, what happens? This aluminum oxide coats this aluminum, form a thin layer on it. It forms a permanent thin layer on aluminum by the aluminum oxide, so the chemical reaction stops, slow down. It is not going to be completely combust. Aluminum cannot be completely combust, oxidized. So that is why directly the enthalpy of the aluminum oxide cannot be determined, because of coat is formed, aluminum oxide coat is formed on the aluminum, and same case for the boron. So due to this reason, enthalpy of these cannot be calculated and written here. Many compounds which cannot be prepared directly from their elements. Some of these compounds cannot be decomposed into their constituents. Carbon tetrachloride example. Some elements do not burn completely due to the formation of protective covering in their surface, just like aluminium and boron. Thus, enthalpies of formation of carbon tetrachloride, aluminum oxide, boron trioxide cannot be determined directly by the calorimetry. So, Hess's law helps us. Is practically useful for determining enthalpy of formation of such compounds. So, dear students, we have here mathematically calculations, numericals. Only you have two topics in this chapter. Very simple. Hess's law, enthalpy chain calculations, yes, and the Born-Haber cycle. Only two topics given in the reduced syllabus. So that's why our syllabus is going to be complete. Last chapter remain. So in next lecture, inshallah, I will solve the numerical problems, but you must solve at home also. So I will solve on the board, inshallah, in the next lecture. So this is about the Hess's law of constant heat summation, adding sum delta H not is equal to delta H1 plus delta H2, so and so forth. So again I am telling you, Hess's law means if the chemical reaction completes in one state from initial to final state function, or it completes in several steps, the sum of enthalpy must be equal to delta H, is called Hess's law of constant heat summation. So thank you very much. Inshallah, I continue in the next lecture for the mathematical calculations of enthalpy of different compounds, indirect method. Hess's law is useful for the calculation of enthalpy of different compounds in indirect form. Thank you very much. We will continue inshallah next lecture.